Okay, looking at my record, the only person I don't have here is Jaron, who was here. Assumably will be back. Okay, the topic on the syllabus today is electric potential. And I really truly hope to get there, but there is a very important topic that is skipped by the textbook. And when I was making out the schedule, I kind of forgot that it was skipped. And that is Gauss's law. So we are going to start with a little bit more on electric fields to Gauss's law, which relates charge to electric fields, and then get to electric potential. So this first picture, the left part is to remind us about the rules of the direction electric field lines go into or out of conductors. What was the rule for the direction electric field lines go with regard to a conductor? They're what? I don't think you said it right. The electric field lines are always normal to the surface. And this figure is to illustrate that if the electric field line was, for instance, vertical on this angled side, then there'd be a force parallel to the surface and the charge could just move along that force. And of course, if there's nothing to stop it, that's what it's going to do. And so the charge will simply move until it reaches a place where the electric field is normal to the surface and it's not being pulled side to side anymore. And so the charge, if you were having the charge distributed so that the electric fields weren't normal to the surface, the charge would simply redistribute itself until you reach that goal. Now the second picture shows you what happens if you just take charge and put it on a non-spherical object, a non-uniform object. And what you see is the charge is distributed so where you have more curvature, you have more charge. Why do you have more charge there? Well, because of the changing direction, you need more charge to make the magnet or the electric fields do that changing. So a result of this, and we haven't done any calculation. In graduate school, we had to do the calculations on the charge density, based on the curvature. But the stronger the curvature, the higher the charge density. And so, as a result, you tend to have the higher, well, let's stick with that right now. The higher the charge density, where you have the stronger curvature. Now, this final picture, picture C, shows a neutral conductor. Now, once again, it's important that we remember these are conductors. These are things the charge can freely move along. If I put it in an external electric field, we still have the electric fields are going to cause charge to move on the surface of the conductor. And so charge will move as a result of that electric field until it distributes itself so it doesn't have any sideways forces. What condition for electric fields means that the charge won't have any forces pulling it sideways on the surface? The electric fields have to be normal to the surface. And so you can see in that picture, the electric fields, instead of having what would have originally been nice straight horizontal lines, the electric field lines have bent around. You've changed the electric field all around because we have that rule. The electric field lines have to be normal to the surface. Lightning rods here. This is a picture illustrating a lightning rod. I know somebody in the lab presentation indicated that there is a limit to the lightning rod effectiveness, I believe. That is the strength of the electric field you can create. And it's probably true there is a limit to how sharp you need to be for a lightning rod. But as a general rule, the sharper the lightning rod, the stronger the electric field you're producing right at the tip. And if you have a strong enough electric field, then that means that the force on the charges in that rod is going to be strong enough that you can actually pull the charge off of the rod. Remember, the force is equal to the electric field multiplied by the charge. And so the stronger the electric field, the stronger the force. And as you saw from just rubbing things, you can rub charge off, you can pull charge off, it just takes a big enough force. And so if you have strong enough electric field, you have enough strong enough force that it ejects charge, dissipating the charge so you don't build up a very large charge on your lightning rod, well, on your object the lightning rod is connected to and protecting. Okay, first question. Why are lightning rods pointed? Choose the primary goal, not the secondary effect, because two of these are true, but one's the primary goal. Guess the front row is the bad place to be with clickers today. Are you able to answer? No. Okay. 11, 2, 3. Okay. 11 people answered what I just said. The primary purpose is to increase the electric field at the point so that charge gets dissipated off. But a secondary outcome is, if you're going to have a lightning strike, it's much more likely to hit that little pointy rod than it is to hit the rest of your building. So that's a secondary effect. So this one here is the secondary effect. All right, I believe, oh yes, I left this in only to prove that I had changed the slide around, but it was like 4 slides later. I forgot to delete the first one when I made the second one. C'est la vie. So that was just there as a, I'm not completely senile, just halfway there. Okay, Carl Friedrich Gauss came up with a brilliant idea. We talked about charge. We draw the electric field lines, and the number of electric field lines going into or out of a charge is proportional to the magnitude of the charge. And the electric field lines always go out of, which kind of charge do they always go out of? Positive charge, and always go into negative charge. So Gauss realized, wait, that means that if I have a box and I just measure how many electric field lines come out of that box, I can tell you how much charge is enclosed. Right? The more lines that come out of the box, the more charge is enclosed. If they're coming out, it's positive charge. If they're going in, it's negative charge. So that's the idea of Gauss's law. We can relate the electric field to the charge that's enclosed. Now, for Gauss's law, we need to calculate this thing that's called flux. The flux has a symbol of capital Phi. Because that's Greek for F, for flux. And the flux is a measurement of how much electric field is coming out of your box. So the actual calculation is taking the area multiplied by the electric field that's coming out normal. Remember, normal is the three-dimensional word equivalent to perpendicular. So if we have a surface, this first surface here, you see the electric field lines are not going in normal. They're going in at an angle. Well, we just take the angle between the surface normal, this here is the surface normal, and the electric field, and that gives us the angle theta. So if we take the component of the electric field that is parallel to the normal, then that is going to be E times A cosine theta. The area multiplied by the electric field strength multiplied by cosine of the angle between the normal to the area and the electric field. That calculates the flux through a surface. Now, Gauss's law is for a closed surface. I have to have a box or something completely enclosing my charge. So to apply Gauss's law, we need to calculate what the total flux is. And according to Gauss, that total flux is just equal to the charge enclosed divided by a constant. Go back to, I think it was Reagan that asked me, how do you determine how many lines to draw? And I said it's arbitrary, but you have to be consistent, right? So if this is twice the charge, it has to have twice the lines. Well, with Gauss's law, what we have is a physical constant, the permittivity of free space, that is essentially the ratio between the number of lines and the amount of charge. I put in capital, bold, and red, it needs to be a closed surface. When we apply Gauss's law, we always have to have a completely closed surface, no holes, so you can go from the outside to the inside. Now here's a real simple question, real simple. Let us suppose that I have a beach ball, and I put this beach ball somewhere where there's a bunch of electric charges around, but there's no charges inside the beach ball. I would have electric field lines that are going, well, let's choose a different color. Electric field lines that are going, like not doing this. What would be wrong about that? They can't cross. Okay, but I've got electric fields doing, funny things. What's the total flux for the surface of that beach ball? Tori gave me a very quick 0. She is correct. Why did she know immediately that the total flux was 0? I mean, I've got a pretty complicated picture. Somebody besides Tori? Austin? Well, that was for a conductor. This is a beach ball. The beach ball is made out of plastic. It's not a conductor, so that's not going to apply here. Anyone else? Yeah, there's no charge enclosed. Gauss's law says that the total flux on the surface is proportional to the charge enclosed. If the charge enclosed is 0, the total flux is going to have to be 0. It would be really difficult to calculate for something like this, but it still has to be 0 in the end. So I don't do the calculation. I say, aha, I know by Gauss's law that it's 0. Excuse me. So how are we going to use Gauss's law? How are we going to make it so it's useful to you, the physics student? Here is the self-same example that I did yesterday. What is the flux through a sphere of given radius that has a point charge of this at the center? How could you find that flux? Go ahead, Austin. Yeah, using the law I just gave you is one of the two ways. Using the law I just gave you, I could say, well, the flux must be equal to the charge enclosed divided by epsilon 0. So that would be minus 2.0 microcoulombs divided by 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared. I don't know what that number is. Somebody want to tell me? I know it's negative. Pretty proud of that math skill. Don't destroy it. Two what? I still didn't hear anything after 2.
Approximately negative 226,000.
That number? Okay. Now in terms of units, the units are going to be, Coulomb is going to cancel with one of these coulombs. Since these are in the denominator of the denominator, they go up to the numerator. Newton meters squared per Coulomb. So that's one way to calculate what the flux is going to be. Yes, Lindsay?
Is the bottom number a constant?
Yes, that is a constant. That is the permittivity of free space. Now, the second way, this way here, it actually didn't matter where the charge was in my sphere. It just mattered that it was inside the sphere. The second way is to calculate directly. And the only way I'm ever going to ask you to calculate it is when you have a nice symmetry that makes it easy. So let me draw a picture to illustrate that. So we have our charge here at the center, and then I have a sphere, which of course on my drawing is a circle. Out here, if that charge is a negative charge, what can you tell me about the electric field lines? They're pointing in. So my electric field lines are going to be going like this everywhere. Now I only drew two of them. You could go all the way around. I just don't want to take the time. What about the strength? If I'm the same distance away from the charge, how is the electric field strength going to vary? It's what? It shouldn't. It should be constant. So the electric field is always going to be normal to the surface and constant strength. That makes my calculation easy. Normal to the surface means that my theta is 0. So the flux is equal to, I need to add up over all the surfaces, but for a sphere I only have one surface. The sum of the electric field times the area times cosine of the angle between them. For a point charge, we learned that the electric field is k times charge divided by radius squared. So there's my electric field. The area, does anybody know the equation for the area of a sphere? It's always on your test, so you don't have to have it memorized. It's 4 pi times radius squared. And then we have cosine of 0 degrees, which is just 1. And so you multiply that through, and you have 4 pi k q. Now that does not look exactly the same as q enclosed over epsilon 0, right? But it is exactly the same. Because by definition, k was equal to 1 over 4 pi epsilon 0. And so if I put in that definition for k, the 4 pi's cancel, and it's exactly the same equation. Now you're probably asking yourselves, really, what's the point of Gauss's law? I hope you're asking that because, why do we learn anything? To have some purpose. The point of Gauss's law is to allow us to calculate the electric field from knowing charge, or the charge enclosed from knowing the electric field. So when we use Gauss's law, we first, for you, actually for the other class too, we always have to have an exploitable symmetry, a symmetry that's going to give me a situation like I just had, where the electric field was parallel to the area, normal to the surface, or the electric field is perpendicular to the surface. So we have to have some kind of symmetry we can use. If there's no symmetry, you're not going to be using it at all. So what type, and you can answer starting now, what type of symmetry does a sphere have? This is very, very simple. Not a tricky question, just to make sure we're following right now, because the next one won't be as straightforward. Woohoo, it worked. All right, so we had 18 said a sphere has spherical symmetry. Yes, indeed. Would have been disappointing if it was otherwise. But you have to identify what the symmetry is, and then you make what we call a Gaussian surface. What's a Gaussian surface? It's a surface you're using in your mind for a calculation. When I talked about the beach ball really had a surface. But when we just did this problem, we didn't really have a sphere there. That was just a sphere I was thinking about. So we call that a Gaussian surface. So quick question. Is a Gaussian surface the surface of an object? No, it is not. The Gaussian surface is the surface of a shape we use for calculational purposes only. It doesn't actually correspond to a physical shape. But we need that shape to match the symmetry of our system. So if our system is a point charge or a spherically symmetric charge, then we'll use a spherical Gaussian surface that's concentric with the charge. Concentric means the center of the charge is the same as the center of the sphere. If we have, let's say, a cylindrical symmetry, then we'll make our Gaussian surface a cylinder with caps on the top and bottom. If we have a planar symmetry, then our Gaussian surface will be, well, actually, I always use the same shape, just with one cap inside and one cap outside. But we have to match our shapes to the symmetry. The charge can be distributed along a line of charge, such as on a wire. It can be distributed on a surface. We have to take those into account, and it's a lot easier to actually do a problem than it is to try to explain any further. So let's look at a problem. First, boy, I hope I have a clicker question in the slide right after this. Our problem is going to be that we have charge spread uniformly along a wire that has charge density lambda. What that means is lambda is equal to the charge per unit length. And then I want to find an electric field some distance away from the wire. What we've learned so far, Coulomb's law, that won't give me an answer. Coulomb's law works for a point charge. It won't work for this. But Gauss's law does work for it. So please, please, please have the clicker question here. Come on. Good. What type of exploitable symmetry does this straight wire have? Okay, everyone has answered, and we had 0, 13, 3, 2. One thing that I actually appreciate is I see that the numbers move toward the correct number sometimes. They were there. It means people answered and then apparently talked to their neighbor and changed it. At least I hope they didn't just copy their neighbor, but they talked to them and said, oh yeah. The correct answer is indeed cylindrical. So going back to my definition of the problem, I have a wire, and I'll draw the wire like, yeah. And it tells me that it's a long, straight wire. Long is a key word. If it's a short wire, I can't pretend to have a symmetry. But if it's a long wire, I can pretend to have cylindrical symmetry. What does it mean to have cylindrical symmetry? It means that if you stay the same distance away from the wire, go around a circle or go up and down, it's not going to change anything. All that matters is how close you are to the wire. If the ends are reasonably close, it's going to matter how, you move up and down, it's going to make a difference if the ends are reasonably close. But if the ends are really far away and you move up and down, it doesn't make a difference. So that's why being a very long wire is important. We usually write the problem saying an infinitely long wire. What's the problem with an infinitely long wire? It doesn't exist. That's a key problem. So what makes it a long wire? It's a long wire if our distance away from the wire, r in this case, is small compared to the distance to the ends. Like if it's less than 1/10 or 1/100th, we're pretty safe. So I have the charge in this wire. So it has charge per length is equal to lambda. Now I'm going to make my little Gaussian surface. My symmetry was cylindrical, so what shape should my Gaussian surface be? A cylinder. So I'm going to make a Gaussian surface that's a cylinder that is concentric with the wire. That means the wire is going right down the center of the cylinder. And now I'm going to apply Gauss's law. When you do Gauss's law, you need to do the left-hand side independently of the right-hand side, and then set them equal. So the left-hand side was the flux. Now, to make my life simpler, before I do this calculation, let me draw the directions of the electric field lines. What directions do the electric field lines go from this wire? Assume the wire has a positive charge. They should go out. Based on our symmetry, the electric field line should be going like this. And the strength should only vary as you get closer or farther to the wire. So if we stay a constant radius from the surface, the electric field strength should be constant. Now let's look at angles. How many surfaces do I have on my capacitor? That's right, I heard the answer. 3 surfaces. 3 surfaces. The top, the side, and the bottom. So let's get the angle for each of these. When I say this angle, what's the angle between? The electric field and the normal to the surface, which saying the surface is a correct way of saying it, but I say the normal too to make sure we're clear what direction it is. So I've drawn the electric fields. In blue, I'll draw the direction for the normals. So on the side, the normal points like this. On the bottom, the normal points like this. The top, the normal points like that. So on the top, what's the angle between my green electric field lines and my blue area normal? 9 degrees. How about on the side? What's the angle between them? 0. How about on the bottom? It's 9 degrees again. So I have my angles. Now, what is cosine of 9 degrees? Cosine of 9 degrees is 0. So that means I'm going to have my electric field times area times 0 for the flux from the top surface and the bottom surface, because the electric field lines are not going into or out of my Gaussian surface on the top or bottom. They're just buzzing it. They're not going in or out. So when I do my flux for the top and bottom, I'll immediately have the flux for the top equals 0 and the flux for the bottom equals 0. That's good because the electric field is varying as you move across the top and bottom because the radius is changing. If that wasn't 0, I wouldn't be able to do this problem. We have one surface left, the side. What is cosine of 0 degrees? Cosine of 0 degrees is equal to 1. So the flux on the side is equal to the electric field on the side times the area of the side. Electric field on the side, I don't know. I simply don't know what the electric field is on the side. What about the area of the side? How do you find the area for the side of a cylinder? Two pi r times the height. If you don't have that at the top of your mind, of course it's on the equation sheet, but all you'd have to think is, if I sliced the side of the cylinder and flattened it out, the bottom would have a length equal to the circumference, 2 pi r, and then you'd have the height for the other dimension. So base times height, 2 pi r times height. So we have, I'm changing colors just to organize a little bit. Area of the side is 2 pi r times the height. I didn't define a height for that cap or that cylinder, did I? I'm not gonna either. Just gonna call it the height. It better not matter, because if it matters, then I could just change my cylinder and get a different answer, and it'd be inconsistent. So it can't matter. So that's the area of the side. The electric field, I don't know. That's what I'm going to try to find. So I'll end up with the left side of my equation. The flux is equal to 0 plus E psi times 2 pi RH plus 0. Top, side, and bottom. So that's the left side of my equal sign. What's the right side of the equal sign in Gauss's law? The charge enclosed divided by epsilon sub 0. How much charge is enclosed by my little Gaussian cylinder? Yeah, I know how much charge per length, and the length that's enclosed is just the height of my cylinder. So the charge enclosed has to be the charge per length multiplied by the height of the cylinder. So the right side is Q enclosed over epsilon 0 is equal to lambda H over epsilon 0. Now I can put those two together. And you see, aha, this H and that H are going to cancel. What do I do with this at this point? Usually the problem would have said, and I think it did, what's the electric field? I'm trying to solve for electric field, so I'll divide across to get the electric field. Okay, notice that K was 1 over 4 pi epsilon 0. So 1 over 2 pi epsilon 0 is 2K. And so that's why I made the substitution for 2K. But what is key here, to me at least, is that the electric field from a point charge, how the electric field changed as you got farther away? Got smaller by what? If you double the distance, how much did it get smaller? Quadruple, because it was inversely proportional to the distance squared. Now it's only inversely proportional to the distance. So if you have a line of charge, the electric field drops off more slowly. What do you think would happen if you had a flat sheet of charge? It doesn't drop off. So let's do that. Let's not just propose the answer. Let's calculate the answer. So I believe this next one is proposing the next problem. Oh, no. This is showing a prettier picture than I can ever draw of everything I've just done. We don't need those stinking better pictures. Which statement is true about the electric field inside a conductor? Wow, Jaron, you were actually right. If there's only 3 answers, that means 1 in 3 will be right. He can be right. He just tries to answer immediately so he doesn't forget, and then he tries to read it, figure out what the answer is, just in case people think I'm mocking him. Okay. Okay. No, there should be one more. Okay, gonna stop now. Okay, so the answers we got were 5, 11, and 1. Now there was not complete agreement here, but there was a majority, and that majority is correct. The electric field inside a conductor is 0. why did I say before that the electric field inside the conductor had to be 0? Yeah. If the electric field inside wasn't 0, if it's a conductor, the electrons can move, and so they're going to have a net force due to the electric field, and they're going to move until you make it so the electric field is zero, so the charges in the center don't move. So it had to be this answer. Now Gauss's law gives us a second way to evaluate that, and I'm just going to do it here. I'm pretty sure I have it in the next slide. But let's say that I have a conductor here. Where is all the charge going to be on the conductor? So all the charge on the outside. Okay, I made this way too big for the density of my plus signs. Maybe I should learn to make faster plus signs. Okay, so there's all my charge. Well, let me take a Gaussian surface in here. What's the net charge enclosed by my little box I made inside of the conductor? It's going to be 0 because all of the excess charge is on the exterior. But if the net charge enclosed is 0, what does the flux have to be? 0. And so it doesn't matter what shape I have, the flux is always going to be 0. The only way it can be true, no matter what shape you have, the flux is 0, is if the electric field is 0. So there's a Gauss's law answer to reiterate the importance there. Because of time, I'm going to skip past this. I want to just look at the picture and talk about the picture and what we can determine from this instead of going through the whole problem. So if I have a situation where I have one charge inside another, where would you see something like this? A lot of us have connected, for instance, a cable modem or a cable to a TV or something like that, and you have this nice coaxial cable. Coaxial cable basically runs on this principle. You have, for the coaxial cable, the outer one is just grounded. What does it mean for it to be grounded? It's what? Okay. It's connected directly into the ground so charge can come on or off as necessary. And then the inner one has your signal on it. So that's actually what we're using is this geometry for those wires. Now those wires, we call them waveguides, and that's far beyond this class. But one of the things that's cool about something like this is if you put a pot, well, based on these arrows, what direction is or what kind of charge do I have on the surface here? I must have a negative charge here. So I have a negative charge, those electric fields are coming in. I can make a Gaussian surface. If this is a wire, so it's a cylinder, I'd make a cylindrical surface. If it's spheres, I'd make a spherical surface. For those of you in Physics 252, you have a problem that has concentric spheres, I believe, as well as one with concentric cylinders. Michaela, for some reason, is really glad she's not in 252. You can make a Gaussian surface that's inside the conductor. What's your flux going to be if you're inside of the conductor? 0. Hence, the charge enclosed is 0. Then I can make a Gaussian surface that's between them. And then I'll have an electric field that depends on the charge that's enclosed. But here's a cool thing. Let's say that we determined that I had minus Q on the inner part. I make now a Gaussian surface that's in the center of this. What's the flux for my blue Gaussian surface? It's 0. How does she know it's 0? Electric field times area times cosine of the angle between the two. The electric field is 0 inside of a conductor. So the electric field everywhere on that blue surface has to be 0. So that means the flux is 0. But if the flux is 0, how much charge is enclosed? 0. So if there's 0 charge enclosed, and I had minus Q in the center, what does that tell me about the inside surface of this? It must be plus Q. And so you can use Gauss's law to see how the charge is distributed. In this case, I knew the electric field because I was in a conductor. So Gauss's law is extremely useful and important in electromagnetism. And yes, you will all have homework problems on Gauss's law. You guys won't use calculus who aren't in Physics 252. Your textbook doesn't have Gauss's law, so you'll come ask me, refer to Hyperphysics, Khan Academy for more information on Gauss's law because our textbook just skipped it. Okay. Yeah, right, we didn't do that problem, so we don't have to worry about the solution. Now we're going to get into, finally, voltages and electric potential. But before we talk about voltage, we have to look at the case of two parallel plates. Two parallel plates, and I put charge that's plus Q on one side, minus Q on the other. Yes, Diksha?
Just going back to that wire question.
Yeah.
Is there a reason why you use the two different equations on both sides of the wire?
Okay, you say going back to the wire like the picture I just did with the coaxial wire, right? Or going back to the problem I worked out?
Yeah.
You always do the left-hand side calculating the flux and the right-hand side with the charge enclosed, and then you set them equal to each other. And so that's why I did them that way. I was telling the students yesterday, oftentimes students simply want to say, well, the flux is equal to the flux, but then you don't have an equation that has any utility. Or they'll say charge enclosed over epsilon 0 must be equal to charge enclosed over epsilon 0. Yeah, I could have always told you that, and that doesn't help me solve anything. That's why I do the two sides separate. Okay, here I have a situation where the geometry actually is going to require, if I have big enough plates compared to the separation, that it's uniform in between the plates. So for physics class, we're always going to make that assumption, that we have the separation between the plates is very small compared to the two dimensions of the plates. In that case, I can make a Gaussian surface here that goes like this. Now, it's a three-dimensional surface, and I'm only drawing 2 dimensions clearly, but it's a box. And that box, if we look at the directions for the areas are on this side going like this side going like this side going like this, and this side going like this. Now, I make it a cylindrical rather than a cubic box simply because that cuts down the surfaces to 3. If I look at the side surface, what's the angle between the electric field and the normal to the surface? If we look at the sides like this one here, what's the angle between this blue arrow and the electric field? 9 degrees. What flux did we already see we get if the angle is 9 degrees? 0. So that means there's no flux for the side of this. Now I said I make it a cylinder because that's going to be true no matter which side, how you're going around. If you make it a cube, you just have 6 sides that have 0 flux instead of 1. What about this side here? What's the electric field for this side here? It's 0, right? Because you're inside the conductor. So that means no flux from this because the electric field is 0. No flux from these sides because the angle is 90 degrees. all you're left with is the flux from this side. And so using Gauss's law, you say, the flux is going to be the electric... got to change back to my pen. The flux is just going to be the electric field on my cap multiplied by the area of my cap, but the charge enclosed is equal to the charge density, the charge per unit area, times the area. Now these are different A's, so A cap. Putting my law together, that's what Gauss's law gives me. I just applied the flux is equal to charge enclosed over epsilon 0. Notice that to solve for the electric field, just divide both sides by A cap, and it gives me this equation. So the electric field between those plates is very simple to derive from Gauss's law. Yes?
Just to confirm, the A that doesn't have the subscript is the area that the charge is spread out over, right?
The A is the entire area of the plate, yes. It's an important thing, yes. So the electric field is equal to the charge on the plate divided by the area of the plate and the permittivity of free space. That comes from Gauss's law. Well, now that we have that, some things to notice. How does the electric field weaken as you move away? There is no over R's in here. It stays constant. The electric field is constant all the way across. If I didn't have this plate here, it would be the same. Right? Because that charge didn't make any effect. So it'd be the same if I didn't even have that. Only the charge that was enclosed mattered. The force on a charge is the charge multiplied by the electric field. So there's going to be a force. If I put a charge in here, like let's say I put a little positive charge right here, there's going to be a force. What direction would that force be? Left or right? Left, she says. Why left? Because it's a positive charge, so it's parallel to the electric field. Force is equal to QE. That's a vector equation. And because I have a force, that means Newton's second law says sum of the force is equal to mass times acceleration. Hence, the acceleration is equal to the sum of the forces over mass, which is going to be Q electric field over mass. And so it's going to accelerate. It's going to speed up. So now we're going to shift to talking about how something moves when it's in an electric field. And in order to do that, we like to talk about its energy. And specifically, we're going to talk about its, that didn't help me any. We're going to talk about its energy per charge. So I'm going to stop on this slide here talking about electric potential energy. Don't worry about doing the concept coach questions for next lecture, because I'm going to, next lecture, be going through mostly that material. That's material that was for today's. So hopefully I'll catch up, but for now I don't want you to be doing problems that are way in the future. I want it to be reading what we're doing. So we'll start next class period talking about the electric potential and those interactions. And I'm actually finishing a minute early because of where we are.